They told you it would take millions of qubits. Millions. Machines the size of stadiums, cooled colder than deep space, running for years before anyone could trust a single answer they gave. That was the future quantum computing promised. And for decades, the future stayed exactly 1 decade away, no matter which decade you were standing in. But this year, a research thread running straight through the University of Chicago's quantum program quietly proposed something that upends that timeline entirely. Not a bigger machine, not a colder one, a shortcut. And if the number holds up, the era of quantum computers needing more qubits than there are grains of sand on a beach might already be over. For nearly 30 years, the entire field of quantum computing has been trapped by a single brutal piece of arithmetic. Qubits, the quantum equivalent of the ones and zeros inside your phone, are catastrophically fragile. A stray photon, a tiny vibration, a whisper of heat leaking through a supposedly perfect vacuum, and the delicate quantum state collapses, taking whatever calculation it was running down with it. The fix has always been the same. Protect one reliable, logical qubit by wrapping it in a small army of physical qubits, all working together to detect and cancel out errors before they spread. The problem is the size of that army. Under the error correction method, most of the field relied on for years, known as the surface code. Protecting a single logical qubit could require anywhere from several hundred to several thousand physical qubits. Scale that up to the millions of logical qubits a genuinely useful quantum computer would need for something like simulating a new drug molecule or breaking modern encryption, and you arrive at a number so large that effectively pushed the entire dream of practical quantum computing decades into the future. Read that again. Not the computer itself, just the error correction wrapped around it was the thing standing between the world and a working quantum machine. This is where the story usually stalls out in most tech coverage, buried under jargon about qubits and cooling and superposition. But what most people are not seeing is that a very specific, very technical breakthrough happening right now inside labs, connected to the University of Chicago's quantum ecosystem, may have just found a way around that wall entirely. And the implications stretch from medicine to encryption to the very AI data centers we've covered on this channel before. According to informed sources inside the field, the shortcut hinges on 2 things working together for the first time at meaningful scale: a new mathematical family of error-correcting codes, and a type of quantum hardware built not from frozen superconducting circuits, but from individual atoms held in place and moved around by beams of laser light. To understand why this matters, you have to understand what Chicago has quietly built into one of the most concentrated quantum research hubs on the planet. The University of Chicago's Pritzker School of Molecular Engineering, its departments of physics and computer science, and 2 of the crown jewels of American national science infrastructure, Argonne National Laboratory and the Fermi National Accelerator Laboratory, all sit within the same regional research network known as the Chicago Quantum Exchange. This is not a marketing label. It is a genuine, tightly wired collaboration between some of the most well-funded quantum physicists in the country, and it has been quietly producing an extraordinary run of results throughout 2025 and into 2026. According to informed sources close to this research community, the foundational mathematics behind the current qubit reduction breakthrough traces directly back to a 2023 paper co-authored by UChicago's own professor Liang Zhang of the Pritzker School of Molecular Engineering, working alongside researchers at Harvard and MIT, describing what they called constant overhead fault-tolerant quantum computation using reconfigurable atom arrays. This is not chaos. This is strategy. 3 years of groundwork, quietly laid, waiting for the hardware to catch up to the theory. And in 2026, the hardware caught up. A new wave of research, building directly on that Chicago-rooted foundation, introduced a family of what scientists call ultra-high-rate quantum low-density parity check codes, QLDPC codes for short, specifically engineered to run on reconfigurable neutral atom arrays. Here's where it gets worse for the old assumptions the entire field had been operating under. Previous attempts at these high-efficiency codes, even when they showed promise on paper, typically achieved what researchers call an encoding rate of only around 10% or less once you tried to run them on realistic system sizes. In plain terms, that means for every 10 physical qubits you built, you were only getting the equivalent of 1 unit of useful, protected quantum information out the other side. The new codes described in this research push that number past 50%. Read that again. More than half of every physical qubit you build is now doing useful, protected work, instead of being consumed entirely by the overhead of protecting its neighbors. The concrete numbers behind this claim are staggering when you actually sit with them. In one demonstrated version of the new code, researchers used 1,152 physical qubits to encode 580 logical qubits, nearly a 1-to-1 ratio, a figure that would have sounded like science fiction under the older surface code approach, where that same 580 logical qubits might have demanded hundreds of thousands of physical qubits instead. In a second, larger demonstration, 2,304 physical qubits were used to encode 1,156 logical qubits, and the logical error rate, the rate at which the protected information actually fails despite all this correction, came out to roughly 1 in 10 trillion per correction round. To put that in perspective, that's a failure rate so low that researchers describe it as approaching what's known in the field as the Terraquap regime, a specific performance threshold associated with running genuinely large-scale, trustworthy quantum algorithms rather than brief laboratory demonstrations. This is the kind of number that 3 years ago, most serious physicists in this field would have told you belonged in a 5-year plan, not a published result. So how does a shortcut like this actually work? This is the part of the story that sounds almost too simple, and according to the researchers themselves, that simplicity is precisely the point. Neutral atom quantum computers work differently from the superconducting chips built by companies like Google and IBM. Instead of etching circuits onto a silicon wafer and cooling them to near absolute zero, neutral atom systems trap individual atoms in place using tightly focused laser beams, then use additional lasers to physically move those atoms around, rearranging them into new configurations as needed. This mobility is the secret weapon. It means the connections between qubits are not fixed in place the way they are on a traditional chip. They can be reconfigured on the fly. The challenge has always been doing that reconfiguration in a way that is fast, reliable, and mathematically clean enough to actually help, rather than introduce new sources of error. The breakthrough tackles this using something called affine permutation matrices, which sounds intimidating, but boils down to an elegant piece of math. Picture every qubit assigned a position in a long line. An affine permutation takes each position, multiplies it by a fixed number, adds another fixed number, and then wraps back around to the beginning if the result runs off the end, similar to how a clock wraps back to 12 after midnight. Do that consistently across the whole array, and you get a structured, entirely reversible shuffle of every qubit's position, one that a laser-controlled atom array can execute using nothing more complicated than a few coordinated row and column shifts. Think about what that actually means in practice. Error correction, at its core, requires constantly checking whether qubits are talking to their correct neighbors, and if not, physically or mathematically reconnecting them. Under older architectures, doing that reshuffling across a large system could require dozens of separate, painstaking movement steps, each one a fresh opportunity for something to go wrong. By mathematically guaranteeing, through the structure of these affine permutations, that any large-scale reshuffle can be decomposed into just a handful of simple, structured moves, the researchers essentially found a way to make the error correction process itself dramatically faster and less error-prone. According to the published estimates, a full round of error checking under this new scheme takes somewhere between 8 and 10 milliseconds, a speed that lines up comfortably with what current neutral atom hardware is already capable of executing today, not some future generation of equipment that doesn't exist yet. Geely paired the BHE-15 with a 308 horsepower electric motor and an AI-driven energy management system that continuously reads driving conditions in real time and decides, moment to moment, whether the engine, the motor, or both together should carry the load. They took the resulting car, the Geely Galaxy M8 Grand Sedan, to a closed test circuit in Hainan province and ran it through a standardized efficiency evaluation. The result, 2.22 liters consumed per 100 kilometers, which translates to 106 miles per gallon in American terms, independently verified by Guinness as a second, entirely separate world record from the engine efficiency milestone, 2 verified records from one car program. Now here's the number that actually makes this real for your own driving life. A typical car with a 15-gallon tank averaging 30 miles per gallon gets you roughly 450 miles before you need to refuel. That same 15-gallon tank at 106 miles per gallon delivers close to 1,600 miles. That's driving from Los Angeles to Denver and most of the way back on a single fill-up. And the comparison that really seals it is Toyota's own showcase. In 2024, Toyota drove a Prius from Los Angeles to New York specifically to demonstrate best-case hybrid efficiency, a carefully planned, heavily promoted run that averaged 92.9 miles per gallon and got celebrated across automotive media as a genuine milestone. Geely beat that number by more than 12%, not with a hand-built prototype or a specially tuned show car. With an ordinary production sedan a customer can walk into a dealership and buy. To be fair, a closed circuit in Hainan isn't the same as stop-and-go city traffic in the snow. Real-world mixed driving will almost certainly land below that peak number, the same way it does for every efficiency claim in the industry. But even discounted for that reality, the gap over the previous benchmark is enormous. Geely's own spokesperson, Victor Yang, stood in front of cameras and said their technology will comprehensively surpass Japanese hybrid engineering, a direct shot at Toyota and Honda, the two brands that have owned the hybrid conversation for 30 straight years And when you actually line up 48.41% against Toyota's 41 and 106 miles per gallon against Toyota's own 92.9, that statement stops sounding like bravado and starts sounding like simple arithmetic. What makes this even bigger, though, is that Geely isn't out here alone. While most Western headlines have stayed locked on the electric vehicle race, an entirely separate and much larger hybrid arms race has been quietly accelerating across China, and most of the auto world hasn't clocked it yet. BYD, the company that recently overtook Tesla as the planet's top-selling EV manufacturer, released its fifth-generation hybrid system back in 2024 at 46.06% thermal efficiency, just behind Geely's new record but still far beyond anything Toyota or Honda currently produce, and BYD's hybrid lineup can already travel a combined 2,100 kilometers, over 1,300 miles on one full tank plus one full charge. Roughly the distance from Miami to Boston without stopping once for either fuel or electricity. Leapmotor, a brand most Americans have genuinely never encountered, hit 45% thermal efficiency in its L7 sedan. Chang'an, Chery, GAC, and Great Wall have all shipped vehicles with combined ranges past 2,000 kilometers within the last 18 months alone. And none of these are concept cars waiting on a future release date. They're sitting on dealership lots right now. Meanwhile, Toyota and Honda's flagship hybrid systems remain parked at 41%, and Ford, General Motors, and Stellantis are still mostly running engines that haven't cracked 35. The distance between 35% and 48% isn't a minor competitive edge, it's a generational leap. The same category jump as tube televisions, giving way to flat screens almost overnight. The underlying technology hasn't improved incrementally. It's moved to an entirely different tier. And here's exactly why this stops being a China-only story and starts affecting what's parked in your own driveway. Geely doesn't only sell cars under the Geely name. Geely owns Volvo outright. Geely owns Polestar. Geely owns Lotus. Geely runs a joint venture with Mercedes-Benz building smart cars. And through a powertrain partnership called Horse Powertrain, Geely actively licenses this exact engine technology out to other global manufacturers. Which means the BHE-15 engine and the IHIV system are not staying inside Chinese borders. This technology is already slotted into Volvo's upcoming product roadmap. It will appear in European showrooms within a few short years, and it will eventually land in American dealerships wearing badges you already recognize and trust, without most buyers ever realizing where the underlying engineering actually originated. Engineering decisions being finalized in Hangzhou right now are going to determine what sits under the hood of cars sold in Los Angeles, Chicago, and New York before this decade closes out, and the ripple effects go well past a number on a window sticker. A hybrid delivering 106 miles per gallon means filling your tank roughly once a month instead of once a week. It means road trips without the low-grade anxiety of hunting for a working charger in a rural stretch of highway. It means no rewiring your garage, no reworking your morning routine, no budgeting years in advance for a potential $10,000 battery replacement for drivers in cold climates, small towns, or anywhere the charging network still hasn't caught up. This isn't a consolation prize. For a huge number of people, it's genuinely the more practical answer for at least the next decade. While the grid and the charging infrastructure slowly catch up to the marketing promises, it's also a real environmental story in its own right. Dramatically less fuel burned means dramatically fewer emissions, without the same mining footprint that comes attached to a large EV battery pack, different path, same direction, real progress either way. And for the industry itself, this is a genuine reckoning. Detroit and Tokyo both built their long-term strategies on the assumption that hybrids were a temporary bridge on the road to a fully electric future. What Geely just proved is that the bridge is far longer, far more capable, and far more competitive than anyone in those boardrooms had actually planned for. So here's the fast version. A boy from a farming village borrows $3,000 to fix refrigerators, gets laughed out of rooms for wanting to build cars, buys Volvo from Ford anyway, becomes the largest individual shareholder in Mercedes-Benz, and 3 decades later his company produces the most fuel-efficient production engine in recorded history, one that sits within 2 points of Formula One performance and gets independently verified at 106 miles per gallon in a car that costs a fraction of what a comparable EV does. Zoom out. And this was never really a story about one clever engine. It's a story about what happens when an entire country stops treating combustion as a dead-end technology and instead treats it as an unsolved engineering problem still worth billions of dollars of obsessive refinement, while the rest of the world quietly assumed the book was already closed. The future of driving wasn't decided in Detroit, and it wasn't decided in Tokyo. It was decided in Hangzhou. And now every major automaker on the planet has to figure out how to respond, whether they're ready to or not. If this opened your eyes to something you hadn't heard before today, the like button and subscribe. Make sure you don't miss what's coming next, and turn on notifications too, because the next story out of China makes this engine look almost modest by comparison. Now I actually want to hear from you. If a hybrid genuinely delivered 106 miles per gallon at a fraction of an EV's price, would that change your mind about going fully electric, or are you still all in on batteries? Drop your answer in the comments below. I read every single one. In 2025, UChicago researchers demonstrated something that sounds almost unbelievable on first hearing. They successfully programmed living cells to function as a biological qubit, blending quantum information science directly into living biological systems, in a genuinely multidisciplinary breakthrough that blurs the line between physics and medicine. Around the same time, a separate team led by physicist Ashish Clerk discovered what they described as a surprisingly simple way to create highly entangled quantum states, the deeply connected particle behavior that underlies nearly every advanced quantum sensor and quantum computer ever built, by making small, precise adjustments to the energy levels of atoms sitting inside an optical cavity, using nothing more exotic than an additional magnetic field or a few extra lasers to fine-tune the relative energy of different groups of atoms. Published in the journal Physical Review X in June of 2026 and supported by the Department of Energy's QNext Quantum Research Center led by Argonne, this work represents yet another example of the same underlying pattern showing up again and again across Chicago's research output throughout 2025 and 2026. Complicated, expensive quantum states and structures achieved not through brute force engineering, but through clever, hardware-aware shortcuts that squeeze far more performance out of equipment that already exists. None of this happened by accident, and it's worth understanding the person whose fingerprints show up across so much of this work. Professor Fred Chong, the Seymour Goodman Professor of Computer Science at the University of Chicago, has spent years building exactly the kind of research infrastructure that makes breakthroughs like this possible. As the lead investigator of a National Science Foundation initiative called Enabling Practical Scale Quantum Computing, and as a member of the 23-person National Quantum Initiative Advisory Committee that directly counsels federal agencies on how to invest in America's quantum research future, Chong sits at the intersection of academic research and national strategy. His lab has set concrete, dated targets of its own, a 60-qubit proof-of-concept machine by 2029 and a 256-qubit ion trap computer by 2033, both explicitly aimed at tackling scientific problems in climate modeling and drug discovery that remain out of reach for even the most powerful classical supercomputers on Earth today. In 2026, Chong was named an ACM Fellow specifically for his contributions to quantum computer architecture, compilation, and optimization. Recognition from one of the most prestigious computing organizations in the world of exactly the kind of overhead-reducing, hardware-aware thinking that produced this year's qubit reduction breakthrough in the first place. So, where does this actually leave the timeline for a genuinely useful quantum computer? The honest answer sits somewhere between the breathless hype of viral headlines and the reflexive skepticism of people who've heard quantum breakthrough one too many times before. A paper co-authored by some of the most respected names in the field, including physicist David Oshlom, published in January of 2026, made an argument that deserves real weight here. Quantum technology, the researchers wrote, is likely following the same long, patient development arc that classical electronics followed decades earlier. One where transformative breakthroughs in lithography and materials science took years, sometimes decades, to move from research labs into industrial production. Patience has been a key element in many landmark developments, the paper states, and it explicitly warns against overheated expectations about how quickly quantum technology will mature. This is the honest concession this story needs before its final push. The qubit reduction breakthroughs of 2026 are real, they are mathematically rigorous, and they are backed by concrete, reproducible numbers that hold up under scrutiny. But they are also, by the researchers' own admission, a foundation rather than a finished structure. Proof that the wall standing between today's quantum computers and tomorrow's useful ones just got dramatically thinner, not proof that the wall has already come down. And that is precisely why this story matters more than almost any other single headline in quantum computing this year. Because for 3 decades, the conversation around practical quantum computing has been dominated by one depressing, unmovable number. Millions of qubits, an army of physical hardware so vast, it made the entire enterprise feel like a permanently retreating horizon. What the research emerging from Chicago's quantum ecosystem and the closely connected work at Quera, Harvard, MIT, and Los Alamos actually demonstrates is that the size of that army was never truly fixed. It was a consequence of the mathematics researchers happened to be using, and mathematics, unlike physics, can be rewritten overnight by a sufficiently clever insight. Reduce the overhead by a factor of 10, then reduce it again with a smarter decoder, Then again with hardware code design from the ground up to exploit the code structure and the multi-decade timeline the entire industry had quietly accepted as inevitable starts to look less like a law of nature and more like an assumption nobody had gotten around to challenging yet. The machines capable of simulating new medicines, modeling the climate with unprecedented precision, or, more unsettlingly, cracking the encryption protecting the world's digital infrastructure, may no longer be a distant next-generation problem. They may be an engineering roadmap with a decade attached to it, built not in some distant future, but in labs connected by a shared research network running straight through the middle of Chicago right now. If you want to understand exactly how close we actually are, and what happens the moment one of these roadmaps crosses the finish line first, that's exactly what we're breaking down next on this channel. So make sure you're subscribed before that video goes live, because this is a story that is moving faster than almost anyone outside these research labs currently realizes. Before you go, I want to know what you think the real timeline looks like. Do you believe a quantum computer capable of breaking modern encryption arrives within this decade? Or do you think the patient, decades-long path to fault tolerance still holds? Leave your answer in the comments below. And as always, I read every single one.